Welcome to the Explainer. This is where we take big, sometimes kind of complicated topics, and we break them down into guides that are just clear and easy to understand.
So today, we're going to demystify probability and the statistical tests that help us make sense of the world around us. We're going to start with the science of chance, then get into the rules of the game. After that, we'll look at a major fork in the road when it comes to data, before digging into both the parametric playbook and the non-parametric alternatives. So yeah, that's our roadmap.
You know, we all face uncertainty literally every single day. Should I take this job? Is this the right move? Well, the beauty of statistics is that it gives us this incredible toolkit for turning all that doubt into a decision that's actually backed by data. It helps us move from just a gut feeling to a calculated risk. Okay, let's dive right into this. And we're going to start by getting a handle on the basic language of chance, which is, of course, probability. At its core, probability is really just a number between 0 and 1. That's it. It tells us the chance that something is going to happen. If it's a 0, nope, impossible. If it's a 1, it's a sure thing. Everything else, all the maybes in life, falls somewhere in between. And that's where we can start to make some really smart, calculated decisions.
So to really get this, we need to know about 3 key building blocks. First, a simple event. That's just a single outcome, like flipping a coin and getting heads. Then you have a compound event, which is when you combine 2 or more simple events, like flipping that coin twice and getting heads both times. And finally, there are mutually exclusive events. These are things that just can't happen at the same time. You can't get both heads and tails on a single coin flip. All right, so now that we've got the building blocks, let's talk about the rules of the game. There are 2 fundamental theorems that pretty much power almost every probability calculation you'll ever do.
First up is the addition theorem. This helps us figure out the chance of either one thing happening or another thing happening. Now, if the 2 events can't possibly happen at the same time, we just add their probabilities together. Simple. But if they can happen together, think about drawing a king or a heart from a deck of cards, we have to subtract the probability of both happening, because otherwise we'd be counting the king of hearts twice.
Next, we've got the multiplication theorem. This one is all about calculating the odds of 2 or more things happening together. If the events are independent, meaning one doesn't affect the other at all, we just multiply their probabilities. But for dependent events, the first thing that happens actually changes the probability of the second. And that's what that P of B/A thing is all about. It's just a way of saying the probability of B happening given that we know A has already happened.
And look, this isn't just some abstract math. These theorems are exactly what you use to solve those classic problems, like figuring out the odds of pulling colored balls out of a bag. And something as simple as whether you put that first ball back in or not, that one tiny choice determines if the events are independent or dependent, and it completely changes the entire calculation.
Okay, so we've got the rules of chance down, but how do we actually use them to test a claim or a hypothesis with real data? This is where we shift from theory into actual application.
And here's the crucial point. Not all data is created equal. I mean, sometimes your data is really well behaved. It follows a predictable pattern, kind of like a perfect bell curve. But other times, it's what we call distribution-free. It doesn't follow a neat pattern, or maybe it's just based on categories. And because of this difference, you can't have a one-size-fits-all approach. You need different toolkits for different kinds of data.
The path you end up taking totally depends on the assumptions you can make about your data. On one side, you have parametric tests. These are really powerful, but they have strict rules. Your data has to follow a specific distribution, like that bell curve. On the other side, you have non-parametric tests. They're way more flexible. They're distribution-free, which means you can use them on almost any kind of data, even simple rankings or categories.
So first, let's explore those powerful parametric tests. Just think of these as the specialized, high-precision tools you get to use when your data is nicely behaved and fits that classic bell-shaped curve. So, if you want to test the average, or the mean, of a group, the z-test and the t-test are your go-to options. Now, the z-test is the real workhorse for large samples, usually 30 or more. But the t-test is more of a specialist. It's designed for those smaller samples, especially when you don't know the standard deviation for the whole population. But what if you need to do something a little more complex? Well, that's where the f-test comes in. It lets you check if 2 different groups have the same amount of spread, or variability. And then there's ANOVA, which is so useful. It's basically like a t-test on steroids. It lets you compare the averages of 3, 4, or even more groups all at the same time.
Okay, but what happens when our data doesn't fit that perfect bell curve? I mean, what if it's all skewed to one side?
or it's just based on categories like good and bad. Well, that is exactly when we turn to the super flexible, non-parametric tests. And the undisputed all-star of this group is the chi-squared test. It is incredibly versatile. You can use it for goodness of fit, which is just seeing if the data you collected actually fits the pattern you thought it would. Or you can use it to check for independence, which is about seeing if two different things are related, like say whether someone's favorite movie genre is connected to their age group.
And here's one of the biggest takeaways of this whole thing. For pretty much every parametric test in the toolkit, there is a non-parametric alternative waiting in the wings. So, the z-test has its counterpart in the sign test. The powerful paired t-test has its alternative in the Wilcoxon signed rank test, and the multigroup ANOVA corresponds to the Kruskal-Wallis test. What this really means is that no matter what your data looks like, there's always a valid statistical tool for the job.
So if there's one thing you should take away from all this, it's that all of these methods, from the basic probability rules to these complex tests, they all share one common goal: to help us find the real, meaningful signal in a world that is just full of random noise, and hopefully to make better decisions because of it. So we've gone on a journey all the way from the basic rules of chance to the two main paths of statistical testing. You now have the foundational framework to look at the world just a little bit differently. So the only real question left is, what patterns will you start to question first?